when Paul invited me, he assigned me the topic of causal inference. He said, take 20, 30 minutes and cover causal inference. And so now that I thought about what I might have to say, I think if things go well, I might be able to run through it twice. Let's see. So here's what I decided I will talk about. I'm going to address three specific questions. Number one, what is a cause? Number two, is causal inference the same as scientific inference? And number three, how can we know when we have identified a cause? Actually, I might run out of time before three, which is the really hard one. Let's see. First of all, what is a cause? So I began not with Wikipedia, but with the Oxford English Dictionary. Let's look it up. So I looked it up, and it says that a cause is that which produces an effect. And it went on to say that cause and effect are correlative terms. Okay, this is not that helpful. So where else to look? Well, this is a symposium about Snow, and I'm a great fan of John Snow. Read his works more than once, and I looked through them again to see what he said. And he actually had a lot of statements about cause, and some of which I was going to show, but decided that it was we're not going to have time to discuss it fully. But one thing that was worth mentioning, I thought, was the footnote that he had in his work on the mode of communication of color, in which he said that various conditions are requisite for the production of a disease, but it is not necessary to dignify these conditions with the name of causes. Now, I speak very gingerly here when I say that I respectfully disagree with this particular comment, because it seems to me that if something is requisite for the production of a disease, that I really want to call it a cause. Well, the thing that motivated me early in my training in epidemiology to wonder about what we mean by causes was a situation that I can exemplify here with this graph. I'm displaying here rates. I made these rates up, but they're kind of realistic. These are rates of head and neck cancer. And the rates are for 4 subgroups of the population. People are divided according to whether they're smokers of tobacco products or drinkers of alcohol. I'd like to focus on the group that is exposed to both, that has a rate of 12 cases per 100,000 person years. Oh, let me say one more thing. That let us assume that there aren't any biases distorting these rates. That is, in the contrast of one rate with another, that these are causal contrasts. So the causation is the only reason that they differ. And let me ask this question, focusing on these people who are exposed to both, who are smokers and who are drinkers. Among this group, what percent of their head and neck cancer is caused by smoking? Well, given the assumption that I gave you, that we can answer this question. We basically put it in what we call a counterfactual question. What would their rate have been? Well, batteries run out. That happens. It's usually not so soon. I'll do this one. No, that's dead too. This one?
Yeah. I'll turn the volume up.
Great. Okay, thanks. If we asked a counterfactual question, what would the rate of these drinking smokers have been if they weren't smokers? It would have been 3. So we can infer from that that out of every 12 cases that occur among drinking smokers, that 9 of them are there because of smoking. So we would say then that 75% of head and neck cancer among smoking drinkers is due to smoking. But we can ask a very similar question about what proportion of the head and neck cancer in the same group is caused by alcohol drinking. And then when we ask the question, what would their rate have been if they weren't drinkers of alcohol, we would say it would be 4. And therefore, 8 out of every 12 cases is caused by alcohol. So we can explain 9 plus 8, or 17 out of every 12 cases, by the 2 causes, alcohol and tobacco smoke. And we haven't ever even covered all the other causes of head and neck cancer, of which there are undoubtedly many. Now, this may sound puzzling. And the reason that I think it sounds puzzling is because most of us are not taught a concept of causation. Most of us teach ourselves what causes mean. We develop a concept of causation when we're very young. It's probably a good survival trait. I think what happens is that at the age, well, maybe going back to infancy, if you think about it, we're born into a world of myriad sensations and experiences. We experience hunger and pain, cold and heat. We see things, we hear things, and we begin to try to put the sequence of experiences together into patterns that we can understand. And at some point, we create an inventory of causal associations. We're all familiar with little kids running around, entering a room they haven't been in before, and switching on the light, turning a switch that they'd never seen before, and making the light go on, quite satisfied with understanding that causal connection, that cause and effect action. Now, as we develop our inventory of causal connections, I guess that what we're doing is also developing a concept of causation, a concept that basically is premised on a one-to-one connection between cause and effect, because that's what's so easy to observe when there's this immediate connection between cause and effect. Unfortunately, this is a naive view of causation, and it doesn't really suffice to get us to the point where we can deal with causes in an appropriate way if we're searching for causes of disease. So the third source that I consulted after the OED and after John Snow was something more familiar to me. It was a paper that I wrote myself. So I was very happy for the opportunity to go back to it. But this was actually, it emerged from a diagram that I drew for myself to help me think through the kind of problem that I just illustrated, which really shouldn't be a problem. When we understand causes in an appropriate way, then it isn't a problem. Now, I've illustrated causes in a way that many people have criticized as being overly simplistic, but I don't take offense at that because that's the way I think, in an overly simplistic way. And I was quite happy to think about causal mechanisms in terms of these pies. Sometimes people refer to this as the causal pies. In this diagram, each pie is a causal mechanism, a complete mechanism, but of course I haven't been able to list all the components of every mechanism. So you have to imagine that there would be many, many more components in every causal mechanism. When we say cause, what do we mean? Well, actually we could mean one of two things when we refer to a cause. We could be referring to a causal mechanism, or we could be referring to these components of a causal mechanism. But when we study causes in epidemiology, the factors that we're looking at are the components of a causal mechanism. So when we say that smoking causes lung cancer, we're talking about a piece of one or more causal mechanisms, a piece of pie out of one piece out of many, in one or more mechanisms out of many. There are a number of insights that I think one can develop based on this admittedly simplistic diagram. I list just a few main ones here. One of them is an effect has more than one cause, and this is true for both senses of the word cause. That is, there's no limit to the number of different mechanisms that could produce a disease, nor is there only one factor in a causal mechanism. Now, the reason that we might grow up thinking that the cause of the lights going on in a room is turning on the light switch is because when we turn on the light switch, all the other causes that are part of that mechanism have already been laid down. If the bulb is burnt out, the light in a room is not going to go on when you turn on the switch. You're not going to get that light to shine until you replace the bulb with a new one. If there's no electric power being supplied to the circuit that the switch would complete, you're also not going to see the light go on. There's a number of factors that you would have to list that would be part of the causal mechanism to get the light to go on. But ordinarily, everything is already there. And all you need to do to complete the causal mechanism is flip the switch. And so we make that inference because there's an immediate connection between the last factor in the causal mechanism and the completion of the mechanism, which is the effect. So we draw that inference, but what we don't appreciate then is all the factors that are laid down before that final factor. So number one insight, an effect has more than one cause, and it's these component causes within the pies that we tend to study as epidemiologists. The component causes interact with each other biologically. That's what we mean, or at least that's what I mean when I think about biological interaction. It means that two factors are playing a role in the same mechanism, and therefore the effect of one will depend on the presence of the other. That's the reason for the head and neck cancer proportions adding up to more than 100%. So the third point that we can infer, this is not a complete list, but the third point is that if we assign what we call an attributable fraction to each of the causes of a disease, there's no upper limit to that sum. They don't sum to 100% because there isn't a one-to-one correspondence between cause and effect. And some cases of head and neck cancer were caused by both smoking and alcohol drinking. So taking away either one would prevent that case. Now, as I say, this is an overly simplistic model. So there are a couple of things that it just doesn't begin to address and wasn't intended to. One of them would be the timing of factors in a causal mechanism. They don't act all at once. They act usually in some kind of time sequence. So that's one limitation. Another one that has been the topic of some great discussion in epidemiologic circles has been the question of whether a cause should have a reference condition. We often talk about causes without much elaboration as to exactly what we mean by the state which we consider to be a cause. So if somebody decides to become a firefighter, should we say that that person has adopted an occupation that might cause a traumatic injury or death? Well, we might think of being a firefighter as being dangerous, but if that person chose that profession instead of being an Army Ranger, it may be that that was a preventive choice because the alternative would have been more risky. And similarly, I saw a headline in the newspaper, rare meat cuts colon cancer risk. Well, you've got to specify a referent here, otherwise you run into the problem of, do you mean that a vegetarian should consider eating more rare meat in order to cut colon cancer risk? But I can't think the intent was that people who are eating well-cooked meat might be at higher risk, and they're the ones who would benefit if they cooked their meat less, not those who are vegetarians and who should start eating rare meat, which raises an interesting and subtle issue about exactly how do we define the state that we want to represent a cause. Well, I'm going to leave this at that point and go on to the second question, is causal inference the same as scientific inference? Here, we don't have to have a lot of discussion. I think the answer is yes. Now, yeah, it makes it easy for me, too. There are causal inferences that are not scientific inferences. I mean, if you're a detective and you make a causal inference to infer who committed a crime, I don't think we would call that a scientific inference. So they're not exactly the same, and physicists wouldn't think that they are making causal inferences. But within the domain that I think most of the people in this room might work, I think that we can equate causal inference with scientific inference without much fear of misdirection. So we're going to leave it at that and then go on to the third question, which is, well then, how can we identify a cause? The point of the second question is that the rules for causal identification are the rules of scientific inference. In researching what I might say about this, I was reminded of the work of David Cheever. I had heard about him, but I did a little more research and I found out more about him. Cheever published a paper that was published on the other side of the ocean in the New England Journal of Medicine in 1860. So he was more or less a contemporary of Snow. He's a bit younger because I think he was a student at the time. It was entitled The Value and the Fallacy of Statistics in the Observation of Disease. Cheever, I didn't know that he became a scion of Boston medicine. When he retired, there was a party that was probably at least this big in Boston, which was kind of interesting because what I knew him for was a quotation. This is a facsimile from the New England Journal 1860 article that I was referring to. And the quote of interest is over here. If you look in the second paragraph, it says, on this slide, it says, an adequate cause, one reasonable of itself, must correct the coincidence of simple experience. And the mere enumeration of any series of events cannot establish general principles without blah, blah, blah. Anyway, this was a caution that was expressed, similar to that was expressed by others, including some famous philosophers, one or two of whom I'll mention in a minute. But look at the sentence before this paragraph. That's the real quote here. He was exemplifying the point that he comes to by saying that it could be no more ridiculous for the stranger who passed the night in the steerage of an emigrant ship to ascribe the typhus, which he there contracted, to the vermin with which the bodies of the sick might be infested. Now, in 1860, of course, they didn't know the cause of typhus. We heard it mentioned earlier today. And I'm sure that had he lived long enough, that Dr. Cheever would have been embarrassed by this quote. Okay, well, it's time for me to get to a dog story. The dog that you see on the right was the dog that my wife and I had and lived with and loved. But as she got older, her eyesight and her hearing were not doing so well. And one day we thought, or maybe rationalized, that it would be a good idea for her to have a seeing-eye dog. And we got a little puppy. We thought they'd be devoted to each other, and you get the idea. But it didn't quite work out that way. The older dog didn't really like the younger dog, growled a lot. And the little puppy didn't remain a puppy. Pay no attention to the girl on the left. The dog is on the right. That's what happened to that puppy. Now, the dog was not that remarkable except for one particular thing. She taught herself to ring the doorbell when she wanted to come in the house. This was kind of a switch on the Pavlovian experiment. The dog rang the bell and the people responded. And this went on for years. That's how she got in, if she were, outside on her own. Now, of course, this raised a question in my mind, is did she make a causal inference? And I've often wondered whether I could just say that the dog, which frankly didn't seem like such a bright dog to me, but of course I was using my own standards and not the appropriate one. Did she do this as a causal inference, or was it just a conditioned response? And what's the difference? That's a real question, is what's the difference? And then I found in some recent reading of a great thinker, Bertrand Russell, where he said, this kind of association, the one I was talking about, is not confined to men, and he meant people. In animals also it is very strong. Domestic animals expect food when they see the person who feeds them. He goes on to call these crude expectations of the uniformity of nature, and they're liable to be misleading. So he says, when the man who has fed the chicken every day throughout its life at last wrings its neck instead, it shows that a more refined view of the uniformity of nature would have been useful to the chicken. Well, frankly, and I hate to disagree with Russell, who I admire so much, but I don't know that it would be that useful to the chicken. Russell was following in the footsteps of the great skeptic David Hume. He was a skeptic of induction. When induction first became popular around the time of Francis Bacon and the rise of modern empiricism, there was great enthusiasm, but Hume managed to dampen some of it with his skeptical outlook that we can't really see a connection between cause and effect. It's not something we can observe. We can just sort of trick ourselves into thinking we've observed it, but we don't really observe it. And he went on to say that sense perceptions are unreliable and that this is all basically a house of cards. He was a great skeptic. Russell wrote later that ever since Hume, the history of Western philosophy has been a history of philosophers trying to refute Hume's skepticism, but they couldn't, so they took great care to write unintelligibly. Or, as Russell put it himself, and this is really quite an elegant demonstration of what we call the scientific method, he said, we have the ordinary procedure of induction. If P, then Q. Now, Q is true, therefore P is true. Now, he's talking like a logician. So P is a proposition that you assume, and Q is a consequence that you deduce from it. And then you observe that Q is true. So, for example, we could say P is the proposition smoking causes lung cancer, and Q is the consequence that people who smoke a lot will get more lung cancer than people who don't. Now, that's true. Q is true. People who smoke a lot get more lung cancer. And therefore we infer that smoking causes lung cancer. But Russell didn't use that example. He used a different one. Continuing the same quote, he said, if pigs have wings, that was his P, well, then some winged animals are good to eat. And, of course, some winged animals are good to eat, and therefore pigs have wings. Russell said that this is what we call the scientific method. Well, this is if you read Russell, I don't think you can be in much doubt that induction as an empirical method is not logical, even though it has its defenders even today. One of the most interesting philosophers on this topic, I think, was Popper, who did much of his life's work in this city. Here he was riffing on Einstein, who said something similar on a slightly different topic, but what Popper said in his seminal work, The Logic of Scientific Discovery, is insofar as a scientific statement speaks about reality, it must be falsifiable. And in fact, insofar as it isn't falsifiable, it's not about reality. He called those kinds of statements metaphysical. He was really aiming at a distinction to resolve Hume's skepticism that you cannot prove something through empirical science. We never prove any statement about nature. But he was making the point that there's an asymmetry because we can disprove statements because of the logic that it's founded on. It's in principle possible to disprove it. Now there's debate about this because people take Hume's other criticisms, such as sense perceptions are unreliable, and everything, of course, even in the refutation, is based on sense perceptions. But nevertheless, there's a lot of food for thought in what Popper wrote. For example, there are others who have written about how the fastest progress in scientific disciplines has been made when scientists have listed out a set of competing hypotheses and tried to kill off the ones that don't work through carefully constructed experiments or studies, ending up with a kind of survival of the fittest hypothesis. Namely, the point is that we make forward progress by falsifying the ones that are wrong, and the ones that are left may be wrong or may not, but they've been tested and they've survived the test, and that's the best we can say about it. Well, my last comment is going to be from Snow. And I think it's an example of what you might consider yet another form of inference that has its adherents, and that would be Bayesian inference, which I think has a lot to offer and a lot to think about. here's what Snow wrote in the same work on the mode of communication of cholera. He said, whilst the presumed contamination of the water of the Broad Street pump with the evacuations of cholera patients affords an exact explanation of the fearful outbreak of cholera, there is no other circumstance which offers any explanation at all. Well, that is, he had a strong prior, I think this is what it means to me, about his hypothesis, and he didn't think that there was much prior credibility in any of the other ones. And I think you could construct this as a Bayesian argument. And I would only add that if you're going to construct a Bayesian argument like that with such strong priors, it's very good to be right. Thank you.